Process control migration strategies, modernizing industrial systems for reliability, OpEx, and future scalability. Executive overview. In 2025, process control system migration is not just a technical concern, it's a strategic imperative. Aging distributed control systems, DCSs, across industries are increasingly incompatible with the demands of real-time operations, predictive analytics, cybersecurity, and digital transformation. While only a fraction of capital projects fund entirely new systems, the vast installed base of legacy automation, valued at over $65 billion globally, must be reevaluated for performance, resilience, and integration with emerging architectures like collaborative process automation systems, CPA, and Industrial Internet of Things, IIoT, platforms. Migration today is more than a hardware swap. It is an opportunity to enable operational excellence and return on assets ROA through better visibility, lower downtime, and support for AI-enhanced decision systems, remote operations, and cloud edge integration. Key drivers now include aging hardware with increasing failure risk, lack of support for modern protocols and security standards, inability to interface with MES, ERP, and cloud analytics, pressure to enable high availability autonomous operations. With suppliers offering increasingly sophisticated migration options, users must develop a tailored risk-managed strategy aligned with their production model, business goals, and operational constraints. Evolution of process automation from centralized to collaborative. Process control has evolved through 3 generations. 1. Centralized control, 1970s to 1980s, rigid architectures, proprietary hardware, software, limited diagnostics. 2. Distributed control, 1990s, 2000s, improved modularity, scalability, and controller intelligence at the node level. 3. Collaborative control, 2010s, present, intelligent service-based architectures with distributed intelligence across controllers, HMIs, and edge cloud interfaces. Modern CPaaS platforms, e.g. Honeywell Experian PKS, Emerson Delta V, ABB Ability, Foxborough IA, Yokogawa Centum, Siemens PCS7 support, multi-layer optimization, real-time control, business KPIs, digital twin modeling and simulation, secure protocol-agnostic communication, e.g. OPC UA, MQTT, Ethernet APL, native integration of analytics, batch execution, and APC layers. For organizations still running legacy systems like TDC 2000, 3000, Provox, RS3, Infi 90, Apax Plus, or early DCSs, migration is the bridge to these next-gen capabilities. Modern migration strategy considerations, 2025 plus. In contrast to past bulldoze and replace models, today's best practices focus on justifying the migration, high risk of unscheduled downtime, lack of compatibility with digital infrastructure, vendor phase-out of support, EOL, EOS notices, failure to meet cybersecurity or compliance mandates, e.g. IEC 6243, need to support new operational modes, remote ops, AI-based supervision, sustainability metrics. Defining the scope. Which systems components are obsolete? Which intellectual assets, logic, I/O, graphics, must be preserved? What levels of system redundancy, analytics, and cyber hardening are required? Selecting the right approach. Phased migration, replace in stages, preserving wiring and cabinets, I/O substitution, plug compatible I/O to minimize rework. Virtualization, host legacy software on modern virtual machines or containers. Encapsulation, use gateways or OPC wrappers to interface with legacy components. Cloud edge coexistence, integrate edge devices for analytics or visualization without full control migration. Leveraging object-oriented and model-based engineering. Modern platforms use object templates, late binding, and digital libraries enabling scalable and reusable designs, reduces loop engineering effort and lifecycle configuration cost. What's changed since 2003? Modern enhancements in migration solutions. Compared to the early 2000s, modern suppliers now offer field wiring preservation tools, plug-and-play I/O kits, automated loop integrity verification, graphics and logic conversion utilities, tools that convert legacy displays and sequence code into native modern formats, ISA 101 standards. Simulation-based validation, virtual commissioning via digital twins. Cybersecurity built-in, support for encrypted protocols, user-based access control, secure boot, and NERC CISA alignment. Edge and cloud-ready architectures, coexistence of plant and enterprise systems without duplication of effort. Additionally, supplier migration toolkits, e.g. Emerson FlexConnect, Honeywell Sure, Invensys FormFit.io, Siemens Migration Toolbox have become more refined and reliable, reducing both risk and downtime. 2025 Outlook and Strategic Takeaways. 1. Migration is a business enabler, not just a technology refresh. Organizations that migrate with the goal of unlocking analytics, batch flexibility, remote operations, and self-optimizing control gain far more than just equipment uptime. 2. Preserve intellectual capital. Rebuilding loops, graphics, and recipes from scratch is expensive. Seek suppliers with proven automatic migration tools and a roadmap for preserving and enhancing existing knowledge. 3. Interoperability and openness matter. Systems that support open standards OPC UA, MQTT, Ethernet APL, ISA 106/88-101 are easier to future-proof and integrate across vendors. 4. Cybersecurity is now a migration driver. Legacy systems often lack patchability, encrypted protocols, and access control granularity. Migration is increasingly prompted by NIST IEC 62443 compliance goals. 5. Virtualization and cloud are reshaping architectures. Controllers remain on-prem, but operator stations, historians, and engineering environments increasingly run on virtual platforms, providing cost savings, disaster recovery, and remote engineering access. Conclusion. Process control migration is no longer a binary decision. It's a multi-dimensional strategy that impacts uptime, scalability, compliance, and competitive agility. With modern tools, modular architectures, and standards-driven platforms, it's possible to execute migrations with minimal disruption and maximum business value. The key is not simply to replace what's old, but to rethink how automation can align with the goals of connected, autonomous, and efficient manufacturing. In doing so, migration becomes a transformation, not a chore. Migration becomes a burgeoning issue when aging systems become a strategic risk and an opportunity. Across the global industrial landscape, migration is no longer a deferred maintenance task. It's an active concern driven by risk, innovation, and necessity. From power plants and refineries to pharmaceutical and food manufacturers, companies are facing an urgent inflection point. Their legacy distributed control systems, DCSs, is often 20 to 30 years old, are holding back modernization, integration, and growth. Why migration cannot be postponed anymore. Modern 1. Increased risk of unscheduled downtime. Many legacy systems are beyond their supported lifespan. Replacement components are no longer manufactured or are difficult to source. System crashes, memory corruption, and I/O card failures are more frequent. Vendors may have issued end-of-support EOS or end-of-life EOL notices, leaving plants vulnerable. In 2024, more than 60% of unplanned downtime events in legacy automation systems were attributed to hardware faults and software lockups in unsupported platforms. Cybersecurity vulnerabilities. Legacy systems were built before the era of cybersecurity threats. They lack encrypted communication, role-based access control, RBAC, patchabilities or secure firmware update mechanisms. These systems are non-compliant with modern standards like IEC 62443, NIST 882, and ISIEC 62443-33. Ransomware attacks on industrial control systems increased by over 80% from 2020 to 2023, with legacy DCS platforms among the most targeted due to weak perimeter defenses. 3. Incompatibility with modern operations and business models. Legacy DCSs typically use proprietary closed protocols, e.g. token ring, RS-485, custom serial buses. They are not compatible with OPC UA, MQT, Ethernet APL, or real-time data streaming to MES, ERP, or cloud systems. This makes them barriers to remote operations, cloud analytics, sustainability reporting, autonomous decision-making. 75% of global manufacturing firms report that outdated automation systems are impeding their ability to adopt predictive maintenance and energy efficiency programs. 4. Lack of vendor support and engineering talent. Fewer engineers are familiar with legacy languages, e.g. ladder logic, basic variants, proprietary function block sets. The generation that commissioned these systems is retiring. Suppliers may no longer provide spare parts, technical support, software updates. The automation talent gap is expected to widen through 2030, making it increasingly difficult to maintain unsupported systems. Shifting market dynamics make migration a business priority. The industrial control market has pivoted. Capital expenditure for new plants has slowed, making brownfield modernization the main path to increased throughput and agility. Automation suppliers now focus less on first-time installations and more on modernization of their own and competitors' systems. Migration projects are now often the core growth segment for automation vendors. Suppliers now compete not only on technology, but also on the smoothness and speed of their migration solutions. The best positioned vendors offer plug-compatible I/O substitution, automated graphic and logic conversion, preservation of field wiring, digital twin-based simulation before commissioning, when migration must happen. ARC advisory and recent industry consensus suggest several clear triggers that necessitate migration. The control system poses a credible risk of downtime. The legacy system limits business innovation, e.g., batch flexibility, cloud reporting, sustainability tracking. Ongoing support or parts are no longer available. The system is incompatible with cybersecurity policies. Integration with new MES, ERP, or cloud platforms is blocked. Operational teams can no longer find expertise to troubleshoot or upgrade. Conclusion. Migration is not optional, it's strategic. Organizations are increasingly aware that not migrating is itself a business risk. While the cost of migration can be significant, the cost of failure, lost opportunity, and extended downtime is far higher. Today's DCS migration is about unlocking agility, securing operations, and future-proofing production. The decision to migrate should not be reactive. It must be part of a long-term digital strategy, one that aligns process automation with the broader goals of resilience, sustainability, and data-driven competitiveness. Migration, therefore, becomes a strategic investment, not just a control system upgrade. Consider migration strategies carefully, balancing technical risk, operational continuity, and long-term value. Once the decision to migrate has been justified, whether due to system obsolescence, cybersecurity risk, or digital transformation goals, the next critical step is to select the right migration strategy. This is not a one-size-fits-all decision. Each facility's architecture, operational constraints, and business priorities will shape what form the migration should take. A well-considered migration strategy must balance risk mitigation, cost control, minimal disruption, and scalability for the future. In 2025, the range of options available to automation users is broader than ever, but with this comes the need for careful planning and evaluation. Share key migration strategy dimensions. Preservation versus replacement, full replacement bulldozer involves completely removing the existing system and replacing it with a new platform. Pros, clean slate, complete architectural modernization. Cons, high cost, extended downtime, greater risk during cutover, not easily reversible. Incremental or phased migration replaces the system in stages, e.g. I/O modules first, then controllers, then HMI. Pros, lower risk, flexible scheduling, better for continuous process plants. Cons, may require interim interfaces or gateways, adds engineering complexity. Hybrid coexistence side by side. New system operates alongside the legacy system using communication gateways or OPC bridges. Pros supports testing, gradual onboarding, and rollback, minimal downtime. Cons can introduce integration complexity, often temporary. Primary migration tactics as of 2025. 1. I/O Connect wiring preservation allows the new control system to interface with existing field wiring via adapter modules or custom cabling kits. Benefits: avoids field rewiring, reduces installation labor and commissioning time, enables loop-by-loop migration. Challenges: physical space constraints, compatibility with legacy I/O racks, mapping errors if signal documentation is outdated. 2. Form-fit I/O substitution involves replacing legacy I/O cards with modern equivalents that fit into the same chassis and use the same connectors. Benefits: no rewiring required, faster cutover, often in a single maintenance window, easy reversion if needed. Challenges: only available from select vendors, may require vendor-specific hardware investments. 3. Gateways and encapsulation. Legacy systems remain in operation, while a new system gradually assumes responsibility for control or visualization via protocol translators or software bridges, e.g. OPC UA wrappers, MQTT brokers. Benefits: enables coexistence and validation, smooth transition with less risk, facilitates short-term integration with MES ERP cloud. Challenges: adds complexity, increases maintenance burden, doesn't eliminate legacy vulnerabilities. 4. Logic and graphic conversion. Many suppliers now offer tools to translate legacy control logic, sequence code, and HMI graphics to the new system's format, often semi-automatically. Benefits: preserves intellectual property, reduces engineering labor, ensures functional continuity. Challenges: may not capture non-standard or undocumented logic. Converted graphics may not leverage new system capabilities, e.g. ISO 101 layout, modular faceplates. Strategic questions to ask before choosing a migration path. What system components are most vulnerable or unsupportable today? Can the field wiring and cabinets be reused? What is the maximum acceptable downtime? Will the migration require changes to safety systems or certifications? Does the migration enable adoption of future architectures, e.g. edge computing, remote access, digital twins? What training and support will be required post-migration? How does the migration impact compliance, cybersecurity, GMP, SIL, etc.? Modern best practices for strategy execution. Digital twin validation. Use simulation environments to test migrated logic and HMIs before go live. Cyber-hardened design. Ensure the new system supports segmented network architectures, RBAC, secure firmware, and IEC 6243 principles. Parallel operation and rollback plans. During phased migration, ensure the ability to revert to the old system in case of failure. Data and historian continuity. Map old tag structures to new systems while preserving historian and batch record integration. Stakeholder engagement. Align IT, OT, engineering, and operations early. Migration isn't just a controls issue. Conclusion. Choosing the right migration strategy is not merely a technical exercise. It is a multidisciplinary planning process that balances cost, risk, time, and future readiness. With today's advancements in I/O substitution, digital simulation, and integration frameworks, it's possible to minimize disruption while preparing for the next decade of automation. Inaction carries its own cost. The longer legacy systems are maintained beyond their life cycle, the more costly, risky, and disruptive migration becomes. Thoughtful, incremental migration guided by a long-term digital strategy ensures resilience, continuity, and opportunity. The cost of change. Unpacking the true investment behind process control system migration. Migration from a legacy control system to a modern platform is not just a hardware upgrade. It is a complex business decision with multidimensional costs. Understanding these costs accurately is essential for setting expectations, securing stakeholder buy-in, and aligning budget with strategic outcomes like uptime, flexibility, and operational excellence, OpEx. While hardware and software may account for only 25 to 35% of total project cost, the majority of expenses are found in the engineering, integration, testing, and commissioning layers. In 2025, successful migrations require a deliberate focus on minimizing not just capital expenditure, CapEx, but also the total cost of ownership, TCO, and lifecycle risks, where the real costs lie. Hardware and software, 25 to 35%. This includes controllers, I/O cards, workstations, servers, and network switches. Licensing for base systems, DCS PLC, SCADA, historians, and operator interfaces. Engineering and batch runtime licenses. Optional tools like simulation, diagnostics, or cybersecurity modules. Although often budgeted first, these costs are predictable and stable compared to the downstream implementation costs. Application engineering and conversion, 25 to 30%. This is where the migration becomes labor intensive. Recreating or converting control strategies, logic blocks, and sequences. Translating or redesigning operator graphics and displays. Revalidating batch recipes, safety interlocks, alarm settings, and custom logic. If the new platform lacks automated translation tools, custom logic must be rebuilt manually, a costly and error-prone process. High-functionality batch or multivariable systems can drive this cost even higher. A 2024 study found that re-engineering complex control logic from scratch adds 35 to 50% more cost versus partial conversion using object-oriented templates. Installation and commissioning, 30 to 40%. This includes physical installation, cabinets, panels, wiring, loop checks and I/O validation, network configuration and testing, integration with third-party systems, e.g. safety systems, MES, Historian. When migrations require field wiring replacement, the cost, duration, and risk increase sharply. Every connection point introduces potential delay and validation effort. Hidden costs to watch. Graphic and HMI conversion. Legacy HMIs often contain years of custom work. Simple duplication does not leverage new UI standards like ISA 101. Graphic modernization can add 20 to 30% more time if not supported by automation tools. Data point mapping, tag remapping, and historian integration are often overlooked. If tag naming conventions change, relinking trends, reports, and analytics may be required. Operator and maintenance training. New systems require training across departments. Training costs vary, but retraining operators on new HMI workflows or alarm systems can affect productivity if not managed well. Certification or qualification, e.g. GMP, ISO, SIL, adds regulatory burden. Downtime and lost production. Even with phase migration, there may be brief process interruptions. Any unplanned delays during cutover translate into lost revenue, often tens of thousands per hour depending on the process. Modern cost-saving strategies. 1. Leverage I/O substitution and wiring preservation. Plug compatible I/O cards, reduce installation time, and preserve existing wiring, minimizing labor costs and risk. 2. Use automated conversion tools. Tools for logic and graphic migration can reduce engineering effort by up to 50% and eliminate human error. 3. Perform pre-migration simulation. Offline simulation using digital twins or emulators can validate control logic, graphics, and alarms before physical deployment. 4. Virtualization and centralization. Hosting multiple operator and engineering stations on a virtualized platform reduces hardware and simplifies updates. 5. Cloud-based engineering tools. New platforms support remote configuration and testing, reducing on-site engineering hours and enabling collaborative development. Key metrics to track. Cost per control loop migrated varies by complexity, 200 to 1,000 plus per loop. Cost per graphics screen converted, $800 to $2,000 depending on interactivity and detail. Cost of downtime per hour, critical for refining, power, or pharma, can exceed $10,000 R. Lifecycle support savings post-migration. Modern systems reduce annual support maintenance by 20 to 40%. Conclusion. The cost of change in process control migration goes well beyond equipment. While upfront CapEx is measurable, the long-term value lies in reduced downtime, improved security, and future-ready architecture. Smart planning, automated tools, and a structured migration path can help control costs, shorten implementation time, and ensure a return on investment, not just in hardware, but in operational resilience, productivity, and innovation capacity. Migration strategies of major control system suppliers. How leading vendors modernize legacy installations for competitive continuity. Today's control system migration landscape is shaped by both the technical complexity of legacy platforms and the strategic positioning of major automation vendors. With billions of dollars worth of aging distributed control systems, DCSs, in place globally, suppliers now compete not just on functionality, but on their ability to seamlessly transition users from outdated systems, either their own or competitors, to modern, scalable, and cyber-secure architectures. What distinguishes each vendor's migration approach in 2025 is not only their toolkits and compatibility features, but also their roadmap for preserving intellectual assets, supporting advanced digital applications, and minimizing downtime and engineering rework. ABB, modular coexistence with industrial IT and ABB ability. ABB's migration strategy emphasizes coexistence, flexibility, and reuse. With numerous legacy platforms under its umbrella, including Infi 90, Mod 300, Symphony, and Freelance, ABB supports incremental modernization through its industrial IT and ABB ability frameworks. Key migration tools and strategies. Aspect Integrator Platform bridges legacy and new systems. Operate AT, HMI, and Control Builder tools support graphical and control logic reuse. Hardware compatibility. Modern AC800M and S800 S900 I/O can run side by side with older controllers. Asset optimization and simulation modules provide operational insight during migration. Strengths. Highly modular object-based architecture. Strong support for batch, electrical, and hybrid process systems, good graphical conversion tools, and late binding. Emerson, Flex Connect, and stepwise migration to Delta V. Emerson focuses on a natural progression strategy from its legacy platforms, Provox, RS3, and competitive systems to Delta V. Its flagship Flex Connect solution and Delta V Connect allow users to preserve field wiring and I/O investment. Key migration features. Flex Connect I/O adapters preserve wiring and terminations. Delta V operate for Provox. RS3 enables HMI continuity. Automated logic and recipe migration. Provox Recipe Manager, Delta V Batch. OPC mirror and serial interface options for early-stage integration. Strengths. Seamless integration of batch, SIS, and historian layers. Wide range of automated tools for configuration and display conversion. Strong service organization for managed migration projects. Honeywell, SurePath, and Experian PKS integration. Honeywell's Sure strategy, support, upgrade, replacement, enhancement, focuses on migrating from TDC 2000-3000, Plantscape, and TPS systems into the Experian PKS architecture with minimal disruption. Key migration elements. The C200i/C300 controllers provide backward compatibility with TDC TPS systems. TPS Station PKS and highway replacement kits allow phase transition. Experian LCN Bridge for integrating legacy networks with modern applications. Loop Scout and Document for diagnostics and documentation during migration. Strengths. High investment protection and wiring reuse. Integration of safety, process control, MES, and historian. Strong cybersecurity alignment with NIST and ISA 62443. 3. Invensys, Schneider Electric Foxborough DCS, form-fit I/O, and non-destructive migration. Invensys offers one of the most non-invasive migration models through its form-fit I/O replacements for legacy systems such as Spectrum, Bailey Infi 90, Honeywell TDC, Emerson Provox, and Siemens Apax. Key migration highlights. Plug-compatible I/O modules that require no wiring changes. Foxborough A2 controllers integrate with Archestre-based platforms. Factory acceptance testing and offline conversion at migration centers. Migration support for Wonderware-based systems via unified visualization tools. Strengths. Fastest physical migration with reversible fallback. Deep integration of historian and MES tools via UVA. Good for complex brownfield and regulated industries. Siemens convergence path to PCS 7. Siemens focuses on structured convergence from more Apax Plus, Teleperm, and other legacy platforms into its modern Somatic PCS 7 DCS. Migration strategy components, faceplate and function block libraries for Apax emulation, database conversion tools for legacy logic and tags. PCS 7 asset management enables predictive diagnostics pre- and post-migration. Profibus Profinet modules support coexisting field devices. Strengths. Strong digital twin and simulation tools, common engineering framework across PLC and DCS, modular expansion and global support reach. Yokogawa, Centum to Centum VP migration with focus on high availability. Yokogawa, with one of the longest-running DCS lines, Centum series, supports phased and project-by-project migration to Centum VP and the Oprex control and safety system. Key migration tools. Automatic control logic conversion from Centum XL CS1000 to VP, graphics replication using visual shell translators, Yokogawa PRM integration for asset and device management continuity, robust options for redundant architecture preservation. Strengths, high reliability hardware with built-in diagnostics, excellent in mission-critical industries, pulp and paper, refining, legacy support extending well beyond 15 to 20 years. Modern trends across all vendors 25. Digital twin usage. All major vendors now integrate simulation tools to validate logic and displays prior to deployment. Edge and cloud integration. Native support for edge computing, historian push to cloud, and MQTT protocols for interoperability. Cybersecurity-centric architectures. Migration paths now emphasize secure by design controllers, encrypted protocols, and compliance frameworks, IEC 62443. Service-based delivery models. Vendors offer managed migration projects, including remote commissioning, asset audits, and lifecycle planning services. Conclusion. While each major supplier offers robust migration paths, the key differentiators lie in field wiring preservation and I/O substitution options, automation tools for logic and HMI conversion, support for phased, non-disruptive transitions, openness and compatibility with enterprise systems. Users should align their migration partner selection with both technical needs and strategic goals, ensuring that the migration is not only successful, but also enables long-term innovation, flexibility, and resilience. Recommendations for selecting a migration partner. Choosing the right ally for a low-risk, high-value control system transformation. Selecting the right migration partner is not merely a procurement decision. It's a strategic alliance that shapes the success of your control system transformation. In today's landscape, where legacy automation systems coexist with IIoT, edge computing, AI-driven optimization, and heightened cybersecurity requirements, the migration partner must bring more than just equipment compatibility. They must bring vision, discipline, and demonstrated expertise. The ideal migration partner helps you protect your investments, minimize operational disruption, and future-proof your architecture for scalable, secure, and high-performance automation. Key factors to evaluate in a migration partner. System openness and integration capability. Can the vendor's platform interface easily with third-party HMIs, historians, MES, ERP systems, and industrial protocols? Do they support standards-based connectivity, OPC UA, MQTT, Ethernet APL, Modbus TCP, Profinet? Can they eliminate or consolidate outdated gateways and custom interfaces? A strong partner supports interoperability and vendor independence, enabling hybrid or multi-vendor migrations. Preservation of existing value. Does the partner offer automated logic and graphic conversion tools? Can they preserve or upgrade your existing field wiring, I/O cabinets, loop documentation, and plant asset management configurations? Are there options for phased deployment or side-by-side coexistence? Preserving intellectual property, such as well-tested logic, operator displays, and batch recipes, reduces risk and cost. Flexible and modular migration options. Do they support form-fit I/O, cabinet retrofit kits, or virtualization paths? Is field device connectivity preserved through protocol bridging or cabling adapters? Are disruption windows minimized through factory staging, pre-tested I/O panels, or plug-and-play I/O adapters? A high-quality partner provides non-invasive migration pathways that align with plant shutdown schedules and operational tolerances. Migration tools, services, and methodology. Do they have a structured, proven migration framework, e.g., Honeywell Sure, Emerson FlexConnect, Invensys FormFit? Do they offer digital twin simulation, loop checkout automation, or pre-migration audits? Are there options for off-site factory acceptance testing and automated graphics control verification? Look for a partner that offers repeatable tool-driven processes that reduce cost, error, and manual effort. Support for advanced applications. Can the new system accommodate or improve existing advanced control layers, e.g., APC, batch, historian, MES? Does the platform support future integration with AI/ML tools, cloud services, and enterprise analytics platforms? Can the vendor migrate or recreate custom applications, scripts, or advanced logic blocks? Migrating a DCS isn't just about base control. It's about preserving or enhancing higher-level performance layers. Training and organizational readiness. Does the vendor offer a training roadmap tailored for operators, engineers, and maintenance staff? Are third-party or IT source trainings applicable, e.g., for Windows-based HMIs, virtualization platforms? Is operator adoption supported with simulation tools or phased cutover? Effective migration is not just technical, it's also organizational. The partner should prepare your team for the post-migration environment. Longevity, roadmap, and platform scalability. What is the vendor's 10-year plus roadmap for the control platform? Do they separate application and hardware life cycles, e.g., via virtualized environments? Is there clear support for future standards, e.g. IEC 61499, containerized control? Don't just migrate to the latest, migrate to the last system you'll need to migrate from. Proven references and migration track record. Has the vendor migrated your specific legacy system before? Can they provide case studies or references in your industry and plant scale? What is their demonstrated performance in risk containment, schedule adherence, and post-startup support? A trustworthy migration partner should be able to show, not just tell, verify success in real-world environments. Checklist, questions to ask your migration partner. How do you plan to preserve my field wiring and reduce installation labor? Do you offer tools to convert my legacy logic and graphics? How will you validate system functionality before go live? Can you simulate control behavior before physical commissioning? What are your cybersecurity hardening capabilities? What support do you offer post-startup? Patches, diagnostics, remote support? What is your roadmap for this platform over the next decade? Conclusion: a migration partner should not just deliver hardware. They should deliver confidence, continuity, and capability. The right partner reduces risk, accelerates deployment, and ensures your system is ready not only for today's requirements, but for the future of smart, connected, secure manufacturing. The decision you make now will shape your plant's agility, performance, and resilience for the next 15 to 25 years. Choose a partner who can walk with you through that full journey, from legacy constraints to digital leadership.